Let's continue practicing setting up the bounds for triple integrals. Here, let's let Q be the solid in the first octant, bounded by the coordinate planes and by the surface x squared plus 2y plus z equals 4. And let's set up the triple integral over this solid of some function f of x, y, and z. I'm not telling you specifically what function because it doesn't matter when it comes to setting up the bounds. Again, I want to emphasize that the bounds describe the solid and that they have nothing at all to do with the integrand. To begin with, let's see if we can sketch a picture of the solid we're talking about. We're only working in the first octant, so I only need to draw the positive x, y, and z axes. And then let's draw the intersection of this surface with each of the coordinate planes. So for example, if I want to find out what the graph is, or the intersection with the yz plane is, I can set x equal to 0. So in the yz plane, I get the line 2y plus z equals 4. And clearly that line has a z-intercept of 4 and a y-intercept of 2. So the intersection with the yz plane is that line segment. Now let's see what the intersection with the xy plane is. To get the intersection with the xy plane, I set z equal to 0, and that gives me x squared plus 2y equals 4. Well, that's going to be a parabola. If we wanted, we could rewrite this as 2y equals 4 minus x squared, or y equals 2 minus a half x squared. So that's going to be a parabola which turns backwards. It's got its vertex over at 2, and then it's turned downwards with respect to the x-axis. So notice that its y-intercept is indeed equal to 2. If I set x equal to 0, I get 2y equals 4, so that means that y equals 2. And the parabola has two x-intercepts, setting y equal to 0. I get an intercept of 2 and also one of negative 2. But we only care about the one which is over here positive, because once again, we're only working in the first octant, where x, y, and z are all positive. So this is meant to be half of a parabola. So it intersects over at y equals 2, which is the vertex of the parabola, and it also intersects at x equals 2. And finally, we can figure out what the intersection with the xz plane is by setting y equal to 0. If y equals 0, I get x squared plus z equals 4. And that's going to be another parabola. Z equals 4 minus x squared. So this is a parabola which is turned downward. It has the vertex up at z equals 4, and it's going to have two x-intercepts. Notice that if I set z equal to 0, I get x squared equals 4, so x is equal to 2 or negative 2. And again, we only care about the 2. So erasing just a little bit of the stuff we don't need right this minute. That's going to be roughly what our shape looks like. So this is going to be curved here in front of, the front surface is curved rather than flat. So let's set this up maybe in two different ways. First of all, let's set it up in the order dz, dx, dy. Most students, if they're given complete freedom as to which order they want to set things up in, they often like putting z on the inside, probably because we have more intuition about thinking about this surface being a graph over the xy plane. So let's take a line segment, put it up through the solid from bottom to top. Notice that it will enter here on the xy plane. It'll continue on the interior until it gets to that surface, and then it continues on the outside. So this part is on the interior. It enters on the xy plane, which of course is z equals 0, and it exits here on the surface. Now remember, the equation for the surface is x squared plus 2y plus z equals 4. And I need to write that in the form z equals. So that'll be z equals 4 minus x squared minus 2y. So my bounds on z are from z equals 0 to z equals 4 minus x squared minus 2y. And then to set up the bounds for x and y, I take this solid and I look at its shadow in the xy plane. So to keep the orientation kind of the same as it is here, I'll make this the positive y-axis and turn so that this is the positive x-axis. And then my shape looks like this, where this is 2 on x and this is 2 on y. Since my next bound is x, I'm going to send a line segment through this way, parallel to the positive x-axis. Notice that it enters here, which is when x is equal to 0, and it exits on this curve. Notice that this curve is exactly the same as this curve in the xy plane, and we learned earlier that was x squared plus 2y equals 4. Now I need to write that in the form x equals, so let's subtract 2y from both sides. X squared equals 4 minus 2y, and then take square roots. X is plus or minus the square root of 4 minus 2y. Since x is positive in the first octave, I need the positive square root. So my bounds on x are from x equals 0 to x equals the square root of 4 minus 2y. And last of all, we do the bounds for y. And notice that y goes from 0 to 2. Once again, to emphasize, if I'm going in the order dz, dx, dy, the z bounds can depend on x and y, the x bounds can depend on y, and the y bounds have to be constants. And that is what happened. The z bounds did depend on x and y, the x bounds did depend on y, and the y bounds were constants. Now let me ask you to set it up in the order dx, dy, dz. And while I erase and clean up the picture, you work ahead of me to see if you can figure out what the bounds are in that order. Okay, let's see. We're putting x on the inside, which means that I need to send my segment through, coming from behind. Coming in from behind, this segment will enter on the yz plane, which of course is x equals 0. It's going to continue on the interior of the solid until I hit the surface, and then I'm going to leave. And remember, the equation for the surface was x squared plus 2y plus z equals 4. Now, since I'm thinking about this surface as being a graph over the yz plane, I need to solve for x so that I can write the surface in the form x equals. So x squared equals 4 minus 2y minus z. And as before, I'm going to take the positive square root to get the portion which is in the first octant. So my lower bound for x is going to be x equals 0. And my upper bound for x is going to be x equals the square root of 4 minus 2y minus z. Now let's project that back into the yz plane. If I do that, I'm going to orient the y and the z so that they kind of look like this picture. I'm going to get this triangular region, which is actually a real live triangle. All three edges are straight lines. And as I've noted here, in this edge in the yz plane is given by 2y plus z equals 4. Okay. Next, we wanted to set up the bounds with respect to y. So I'll draw my line segment parallel to the y-axis, entering on the z-axis, and exiting on the slanted line. The z-axis has equation y equals 0. And solving for y in this equation, I have y is 4 minus z over 2. So my y bounds enter at y equals 0 and exit at y equals 4 minus z over 2. And then finally, my bounds on z are from 0 to